Hello guys, nice to see you. Hi. So last time we discussed and considered the Biot-Savart law, which helps us to calculate the magnetic field vector based on the direction and magnitude of electric current flowing through some wires. And so it actually defines also the orientation of magnetic field and its magnitude. And we did some calculations based on different systems in order to see the practical application of Biot-Savart law, how it can be used to do some calculations of electric field vector in different points around electrical conductors carrying electric current. So today we proceed further with learning new features of magnetic field, and we will start with interaction between two wires, which with some electric current, how they interact with each other per unit length. And afterwards, today we will cover also Ampere's law, which is another important topic in field of magnetism. Okay, so let us maybe first I share my screen to show some figures. Okay. So we know that if we have some current flowing through electric wire, so it's possible to determine the orientation and magnitude of magnetic field vector. So in this particular case, it will be such a circular structure around the wire. So if this sum is directed towards the electric current of the right hand, then this curved four fingers, they show the orientation of the magnetic field around this electric wire with electric current. And for instance, here we see with these small iron pieces, kind of tiny compass needles, we can see the circular structure of the magnetic field around a straight wire with electric current flowing through it. So means that if, for instance, we don't have any current flowing through conductor, if we place these small magnets, like small compass needles next to the wire, they will be oriented along the weak magnetic field of the planet Earth. And once we turn on the electric current flow through this wire, the magnetic field created by this current is considered to be much stronger than the magnetic field of our planet. So we can neglect with the last one. And then all these needles will start to orient along the magnetic field lines around this conductor with carrying electric current. So what we can do next, we can try to integrate, like over closed loop, integrate the scalar product of this magnetic field vector and ds vector along this closed circular loop, and then show what it will be equal to. Based on this, we will be able to derive Ampere's law. However, before we proceed with this, so we will come back to this point again. I just wanted to recall what we learned previously and what exactly we will do in order to get the to get to this point of considering Ampere's law. But first, we need to quantify the interaction between two long wires. And in order to do that, let us now stop sharing this image. And let me change the camera. Yeah. So let us consider two long wires. So they are located at some distance A from each other. So this will be wire 1 and wire 2. Then we have also some lengths of these wires. We have electric current flowing through both of these wires, so it I1 and I2. They are flowing in the same direction. So first, our question is, what will be the force F1 acting on a conductor like wire 1 from the side of wire 2. And for this purpose, we need to show orientation of magnetic field vector, which is created by wire 2 in this point where we want to calculate the force. And we know from previous lecture that magnetic field of long wire next to it will be calculated with this equation. So B2 is equal to mu naught times I2 divided by 2 pi a. So this is a distance from the wire to the point where we want to determine the magnitude of the magnetic field, and mu naught is permeability of free space, and I2 is the magnitude of electric current. So we keep this in mind, so we will come back to this. And also we can express this force F1 as the product of I1 times L vector, like vector product with B2 vector, which is with the magnetic field vector created by conductor number 2, wire number 2. So taking into account that L vector is perpendicular sorry, to B2 vector, we can write that absolute value for this force 1 will be equal to the product of I1 times L, length of this wire, and times B2. magnitude of the magnetic field vector. So in this case, we can substitute B2 with its expression. So this will be equal to I1 L times L times this expression mu naught times I2 divided by 2 phi like pi a, and this will be equal finally to mu naught I1 times I2 over 2 pi times a times L, length of these two wires. So this is the expression for the force F1, which we like magnitude of this force F1, and we know from the third law of motion, third Newton's law, that F2, let's show here some force F2 will be the same in absolute value, but different, opposite in orientation. So it will be equal to minus F1 vector. So this will be F2, it will be force exerted on wire number 2 because of the magnetic field created by current flowing through wire 1. And that's why for absolute values, F1 will be equal to absolute value of F2, and we can call it just some FB, magnetic force. So it's convenient to present normalized magnetic force per unit length of wires, since it doesn't take into account then some specific length of these wires. So we can write that FB is divided by length is equal to mu naught times I1 times I2 divided by 2 pi a. So this is the kind of final equation which describes interaction of two long wires with electric current flowing through them in the same direction. So that means that they will, in this case, actually in absolute value, it's just a final equation, but what we need to highlight that if electric currents are flowing in the same direction as shown on this image, we see that these wires are attracted to each other. If direction will be in opposite, so if electric currents will flow in different directions, then these electric wires will repel from each other. So this should remember. And by the way, this feature of interaction between two long wires is used to specify the like calibrated value of 1 ampere, which defines, so definition of 1 ampere, it's when two long wires separated by 1 meter interact per unit length with force of 2 times 10 to minus 7 Newton per meter. So that is actually the definition of 1 ampere in the international system of units. So this particular case, which we considered here, has a very important practical value, since it defines ampere, which is one of the key international system units, which are used to describe a lot of processes in electromagnetism. So now we come back to our discussion of Ampere's law. So maybe I share my screen once more. So to recall you that we have a system with electric current. We have this magnetic field around it, and our purpose now is to calculate the loop, like linear integral along this closed loop of the scalar product of magnetic vector and ds vector. So now we switch the camera and can start writing. So this integral, linear integral over a closed loop is shown like this. And we have scalar product of magnetic field vector and ds vector, a small displacement vector along this trajectory, along this closed loop. So we assume that at each point of this closed loop, which we consider, magnetic field is uniform because of the symmetry of the magnetic field around a wire with like carrying some electric current. Then we can write that B is outside of integral, and here is ds. So also we, as you notice, we don't have vectors here anymore because the scalar product, let's say B times ds is equal to magnitude of vector B times magnitude of vector S ds times cosine alpha, which is angle between vector B and ds. Since when we integrate along this closed loop, vectors B and is like vector B is parallel always to vector ds, so alpha is equal to 0, and that's why cosine alpha is equal to unity. So we don't need to take anything else into account. So here we can now write the expression which we already mentioned on previous slide for magnetic field, like magnitude of magnetic field vector next to a straight long wire with electric current, that is mu naught times I over 2 pi. Here we put r, it's like distance from the wire to the point on the closed loop, and this is actually the radius of this circle which we integrate along. And then integral over this closed loop will be just length of the circle, and that will be 2 pi times r. So if we now see here what happens, we cancel out our denominator, and we end up with mu naught times I. So this is actually the form of introducing Ampere's law. So integral of the scalar product of magnetic field vector and ds vector this integral along a closed loop is equal to the product of mu naught to electric current I, which in this case is the steady state total current passing through any surface bounded by the closed path, like this loop, which we consider in the integral. So this is a mathematical expression of the Ampere's law. And this law has some similarities with the Gauss law in electrostatics, because Ampere's law is used to determine magnetic field created by different combinations of electric currents. So similar to Gauss law, which is used to calculate electric field created by different systems of electric charges. And also it really helps a lot to apply this Ampere's law to calculate magnetic field in case when there is some symmetry of the problem. So when there is some spherical or cylindrical symmetry, that is kind of very beneficial case for application of this law in order to calculate magnetic field. So now let us do some examples. And let us consider a wire, some long wire with electric current I flowing through this wire. And our question will be, what will be the magnetic field, like magnitude of magnetic field vector at the circle with radius r around this wire, assuming two cases. R is larger than radius of the cross section of this wire. This is our radius of the cross section. And another case will be R is smaller than radius of the cross section. So our so-called Ampere's loop will be in this case with a diameter r smaller than the radius of the cross section of this wire. So let us first consider this larger case when we have radius of the Ampere's loop larger than the radius of the cross section of the wire. So when we address this first question, again we need to deal with this integral over closed along closed loop of the scalar product of magnetic field and ds. So in this case, this is the s vector. Again, they are parallel to each other. That's why we can deal with absolute values. And this will be equal to b times 2 pi r, the length of this Ampere's loop will be equal to the integral over along this closed loop ds, and this is 2 pi times r. And we know from the Ampere's law that this should be equal to mu naught times I, as shown here. So now if we solve for B, R, we can write that it's equal to mu naught times I over 2 pi R. And this is like familiar equation for us because we already derived this magnitude of magnetic field around a straight conductor, long wire previously, but this time we did it applying this Ampere's law. And this is valid for radius of the Ampere's loop larger or equal to radius of the cross section of this wire. So now let us consider a bit more interesting case when we have radius of the Ampere's loop smaller than the radius of the cross section of this wire. So let us go to another slide. And in this case, we need to recall what states the Ampere's law. So electric current in like right side of Ampere's law is a steady state total current passing through the surface defined by this closed path and so-called Ampere's loop. So in this case, when radius of this Ampere's loop is smaller, not all current I is flowing through the surface defined by this surface, so through the surface defined by the closed loop, and only part of it, assuming that we have uniform distribution of electric current density across the cross section of this wire, we can write the following. So, and first claim that there is some certain current I prime which flows through the surface defined by the closed Ampere's loop, and for sure this current is smaller than current I. But if we assume again this uniform distribution of the current density along the cross-section area, we can write that the ratio of this I prime to I will be equal to pi times r square, the area of the defined by the closed loop divided by p times r capital square, which is the area, cross-section area of the wire. And in our condition now, we assume that r is smaller than r capital. So from here, we can solve for our unknown current I prime, which flows through the surface defined by Ampere's loop. And that will be r squared over r capital square times I. So this we keep in mind. And again, we apply Ampere's law. So we have linear integral cross closed loop, Ampere's loop of the scalar product B vector times ds vector. This is equal again as previously to B magnitude of magnetic field vector times 2 pi r, the length of the Ampere's loop, with the radius smaller than the radius of the cross section. And from Ampere's law, we know that it should be equal to mu naught. And here, instead of I, we need to put I prime, because this is the current which flows through the surface defined by this closed Ampere's loop. And that will be equal to B times R square over R square times I. And solving from these conditions for magnetic field vector magnitude, it will be mu naught times I over 2 pi r capital square times r. And this is valid when r is smaller than r capital. So now what we can do in terms of analysis of our results for two different conditions, it's kind of nice to have some visual representation. So let's say it will be magnetic field versus distance from the wire. So here we have this distance r is like distance from the center of the wire. So here is the radius of the cross section of the wire, and we, as we shown on the previous slide, so for distance larger than the radius of the cross section, we have one, like the magnetic field is proportional to 1 over distance. So we can come back to this slide, and here it will be something like this. So when a distance is larger than the radius, it is proportional to 1 over r. However, when distance is smaller, so we are still inside the wire for this second condition, we see that magnetic field is proportional to the radius, and so like linearly proportional. So here we just have a straight line. So this is how magnetic field changes with the distance from the center of the long wire. Okay, so this part we already considered, and now we proceed further with the calculation of magnetic field of a solenoid. So let us go to another slide, and let me share the screen. Oh no, where it is? 1 second. Share the screen. So solenoid is a long wire in the form of a helix, and with this configuration of like arrangement of wire, it's possible to get quite reasonably uniform magnetic field in the space surrounded by the turns, like this, turns of the wire. So this area surrounded by turns is called interior area, and area outside these turns is exterior area. So definitely one of the most important features of solenoids, it's a possibility to obtain quite uniform magnetic field of like in the interior area of this solenoid. So it depends on how long this solenoid is. It's like distribution of magnetic field lines of a solenoid is kind of very similar to distribution of magnetic field lines of a permanent magnet. So we also see that we can consider some south and north pole for solenoid similar to the permanent magnet, and in the like in this area in the middle of the solenoid, in the exterior region outside the space limit, like defined by these turns of the wire, magnetic field is has some cylindric like spherical symmetry. So of course, it's easier to consider some ideal case, and so-called ideal solenoid is a solenoid when we have the ratio much larger than unity of the length of solenoid to the radius of the solenoid. So radius of this area of the like radius of the interior area, which is defined by turns of this wire. And if this radius of the solenoid is much smaller than the length of the solenoid, then we can consider that the magnetic field in the interior area of the solenoid is quite uniform, and then it's easier to do some calculations with this. So from the we can consider here two loops, like Ampere's closed loops, and if we consider loop 1, it is possible to show that magnetic field outside the solenoid in the exterior region is quite weak, because for this case we have only current I, which flows through this wire, which forms the solenoid. And if we take a look on this surface defined by closed loop, this current is flowing upwards, and it's just current I. We don't have any repeating multiplication of this current. So this current is quite small. It's just taken once, this magnitude of electric current, and that's why magnetic field outside the solenoid is relatively weak. However, magnetic field inside is caused not just by one wire, but when we have a solenoid made of turns of wire located very close to each other, like shown on this image, we can consider one turn as a closed coil, like some closed current loop. And obviously this, as we have shown previously, such coil with electric current will create certain magnetic field. So the thing is with solenoid that we have many of these coils attached to each other, and magnetic field inside solenoid will be a vector sum of magnetic field vectors created by each of these coils. So we add them up, and that's why strength of magnetic field in the interior region of the solenoid is quite strong. So it is possible to consider this rectangular closed loop in order to calculate the strength of magnetic field inside the solenoid. So we obviously also need to apply Ampere's law, and when we and that is based on integration along like closed loop. But here we can, since it's rectangular structure, we can define different segments of this loop, and for instance, integral of the magnetic field vector scalar product to the ds will be equal to 0 when we consider segment number 3. So because magnetic field is perpendicular to this segment, and outside the solenoid, also that is true for magnetic for this integral along side 2 and side 4 of this closed loop, and eventually we have only side 1. So sides 2 and side 4, they are also always perpendicular to magnetic field, both for the internal and external area of the solenoid. And there is only one side of this rectangular loop where the integral is not equal to 0. So this is along side 1. Let us come back to the our slides where we can start writing, and we can show that integral of the scalar product B vector times ds vector is equal to integral of this scalar product only along path 1. And this is equal to B times integral ds, again, because for path 1, vectors B and ds are parallel. So cosine of angle 0 is equal to unity. So here we write path 1, and this will be equal to magnetic field B times L, because this integral along path 1, it will give us the length of path 1, which is L. So now, since we already know this, what it will be equal to the this integral, we know also that on the right side of Ampere's law, there is a total steady state electric current which flows through the surface defined by this closed path. So let us share this image again, and we will see what is the total electric current. So we see that from this side, in these coils, which form the solenoid, electric current is directed from us towards the plane of the image. And we see that there are many coils which are in the area defined by this closed loop. So in this case, we need to calculate total number of these coils in the loop and multiply them by I, because I is the electric current which flows through the wire, and in each of these loop there is the same current which will additively contribute to the total current flowing through the surface defined by the closed loop. That's why now we stop sharing. That's why we can write that this integral is equal to mu naught times this total current, which will be n number of turns, like these coils, which are overlapping with the surface defined by Ampere's rectangular closed loop, which we considered, times I. So now we have final equation, this for Ampere's law of B times L is equal to mu naught times N times I. And from here, we can easily calculate the magnetic field. So B is equal to mu naught N over L times I. And this can be written as mu naught times Ni, where this N is equal to total number of turns divided by length of the side of this closed loop, like side 1. So actually it gives us the density of these turns per unit, number of these turns per unit length. And this is the final equation, which gives us the magnetic field vector amplitude in the interior region of the solenoid. So before we finish for today, we still have some time. It would be good to introduce another important concept, which is Gauss law in magnetism. And so technically we will calculate the magnetic field flux through some area. So magnetic field flux is equal to the integral of magnetic field vector scalar product with dA vector. And let's say if we have some surface, on this surface we have some small surface element. So this perpendicular to the surface element will be dA vector, which has direction of the normal unit vector, and its magnitude is equal to the area of this small surface element, which is dA. And then we have some magnetic field vector B and some angle theta between them. So we can write that some small magnetic field flux through this small surface element would be equal as B times dA times cosinus theta. So d f b will be equal to 0 if this angle theta is equal to pi over 2, like 90 degrees. If the magnetic field vector is perpendicular to the dA vector, this which defines area and orientation of the surface element, then magnetic field flux is equal to 0. And also magnetic field flux dB is equal to B times dA when our angle theta is equal to 0. So when these vectors are parallel, then the magnetic field flux is equal just to the product of magnetic field and area of the segment of surface which we consider. So I think that now we already are running out of time. There is one example for calculating the magnetic field flux through a rectangular shaped surface next to a long wire with electric current. But I believe we will do that shortly at the beginning of our next lecture in like on Friday, and we will start considering on Friday magnetic properties of materials, because definitely present. So far we were considering only empty space, like vacuum. However, similar to the electric constant of some materials which can be used to fill the space between plates of electric capacitor, they will influence on the magnetic field, like magnitude of electric field vector. In the same manner, presence of some material with certain magnetic properties will also affect on the magnitude of magnetic field vector, and that we will consider on our next lecture on Friday. Thank you very much for attention. Have any questions?
Thank you. Goodbye.
Yeah, have a good evening. See you next time. Bye-bye.